Welcome back to graphing polynomial functions from factored form. We're going to take a look at the next example. We have the function n of x equals x minus 2 to the power of 3 times x plus 3 to the power of 1. And we need to draw a sketch of this graph just like we did in example number 4. So I ask that you try this on your own. So you may want to try this first and then you can consult with this explanation, so with this video. So let's get started again. So we're going to take care of the exponent. So the exponent of the first factor is 3. The exponent of the second factor is 1. That will make the degree of this polynomial function equal to 4, which means that this is an even degree function. So we're looking into coefficients. The coefficient of x is 1, coefficient of x is 1. So the leading coefficient in this case would be equal to 1 to the power of 3 times 1 to the power of 1. That is positive 1, so that's a positive leading coefficient. So being an even degree function with a positive leading coefficient will make us think that this graph will show the same end behaviors as the parabola, second degree polynomial function, right? With that opens up, so positive leading coefficient, which means that this graph should be starting in quadrant 2 and end in quadrant 3. Next, we need to determine the x-intercepts, which means that we have to make each factor equal to 0. So if x minus 2 equals 0, then the first x-intercept will be at 2. X plus 3 equals 0 means that the next x-intercept will be at negative 3. Now, whenever we state the x-intercepts, we have to look into the order of the intercept, which depends on the power of the factor where x-intercept came from. So if the power is 3, that means that this would be a third order root. And the power of the factor x plus 3 is 1, which makes x equals negative 3 a first order root. So the y-intercept is also helpful to determine before we sketch the graph. And for the y-intercept, we always set x equal to 0 and evaluate y. So that means we have 0 minus 3 to the power of 3 times 0 plus 3, which is negative 3 power 3 times 3. That's negative 27 times 3, and that is 81 negative. So I'm going to say that negative 81 is somewhere in here. That's the y-intercept. I'm going to plot the x-intercepts on the x-axis, obviously. So we have 1 at x equals 2. And 1 at x equals negative 3. So here we go. 1, 2, 3, negative. So knowing that the graph will start in quadrant 2 and in quadrant 3, I can start sketching. And I will say that I have to start in quadrant 2, make sure that I hit x equals negative 3. Now, consult with the order of the root. That's first order, which means the graph will cut through x equals negative 3. Now, next, the graph will have to make a turn somehow because we need to go back to the next x-intercept. And on my way back, I make sure that I go through y equals negative 81, which is our y-intercept. And I move towards x equals 2. And before I get there, I need to check the order. That's a third order root, which means that at x equals 2, the shape of the graph will be an S shape or an inflection point. So what that means is that the graph of this function is going to look something like this at this point. And that's how I shape the graph of this function. Okay, here we go. So all the conditions are satisfied, so the end behaviors are correct, the roots are there, a first order and a third order root, the y-intercept is here. Obviously, we don't know exactly how far down or up we could have gone in here, but we are just sketching again this function, so we are not really graphing it. So all the features as described are in this beautiful picture. All right, thank you very much for learning with me again, and thank you for listening. Bye for now.